We will now discuss the parallel axis theorem. The parallel axis theorem gives us a method of finding the moment of inertia of an object about any other axis other than the axis that passes through the center of mass. For example, you know that the moment of inertia of a disk about an axis that passes through its center of mass is 1/2 mr squared. Is that right? Okay, if you know the moment of inertia about an axis through its center of mass, then you can find the moment of inertia of that object about any other axis, as long as you know the perpendicular distance between the new axis and the axis that passes through the center of mass. Alright? And that is what parallel axis theorem gives you. Alright, let's have a look what parallel axis theorem says. If I center of mass for an object is known, means moment of inertia of an object about its center of mass is known, then we can find the moment of inertia of that object about any other axis that is parallel to that axis. In other words, the parallel axis theorem is useful only to find the moment of inertia about an axis that is parallel to the axis through the center of mass. That's why it's called the parallel axis theorem. The new axis that we consider must be parallel to the axis that passes through the center of mass. Alright, now here I have an object. This is the axis that passes through the center of mass. And this is the new axis about which we need to find the moment of inertia. And this axis is at a distance h, the perpendicular distance between the new axis and the axis through the center of mass is h. So the figure shows an axis passing through the center of mass of the object and another axis that passes at a distance h from the axis through the center of mass. So the distance between that two axes is h. According to the parallel axis theorem, the moment of inertia I of the object of mass m about this parallel axis is I equal to I center of mass, that is moment of inertia about this axis that passes through the center of mass, plus mh squared, where m is the mass of the object and h is the perpendicular distance between the two parallel axes. Very simple theorem, but it is useful to remember because this is going to be used not only in physics 1 but also in physics 2. Very important to know that. Alright, let's use that in a situation. Find the moment of inertia of the ruler of negligible thickness shown in the figure about a perpendicular axis passing through its left end. This is a ruler of negligible thickness. Well, we know the moment of inertia of this ruler about an axis through its center of mass. Tell me, what is the moment of inertia of a ruler about an axis through its center of mass? What's the formula for that? It's 1/12 ml squared. In other words, I center of mass is 1/12 ml squared. If the length of the ruler is L and its mass m, the moment of inertia about its center of mass, about this axis, is I center of mass is 1/12 ml squared. we have been required to find the moment of inertia about an axis that passes through one of its ends. Alright. Since L is the length of the ruler, the distance between the axis through the end, if an axis is passing through an end, what is the distance between that axis and the axis at the center of mass? It will be half of the whole length. So H equal to L over 2. So this is the new axis. And for that new axis, this is H, the perpendicular distance between the two axes. And that H equal to L over 2. Alright, what does the parallel axis theorem say? It says the moment of inertia of this ruler about the axis through its end is moment of inertia about the center of mass plus mh squared. Alright, now I center of mass is 1/12 ml squared, there you are, plus mh squared, replace your h by L over 2. So that will be 1/12 ml squared plus m times L over 2 squared, and that will be 1/12 ml squared over 12 plus ml squared over 4. And what is that equal to? That will be 12 common denominator, that will be 12, it will be 3 ml squared plus ml squared, that will be 1/3 ml squared. So the moment of inertia of the ruler about an axis through its end is 1/3 ml squared, whereas the moment of inertia of that ruler about an axis through its center of mass is only 1/12 ml squared. And if you notice, this 1/3 ml squared is 4 times 1/12 ml squared. So if you want to rotate this ruler about one end, it's going to be very hard, because the moment of inertia of this ruler, you see, I can't even hold it there. The moment of inertia of the ruler about an axis through its end is 4 times the moment of inertia about an axis through its center of mass. Okay. Let's now talk about work done by a torque. Now, if you notice, for every term that we use in linear motion, there is a corresponding term in rotational motion. Tell me, what is work done in linear motion? In linear motion, work done is force multiplied by the linear displacement, F times x. So what do you think will be work done in rotational motion? Well, I'm sure most of you know it. Work done by a torque. You see, in the case of linear motion, work is done by a force when it produces a linear displacement. In rotational motion, work is done by a torque when it produces an angular displacement. So, work done by a torque is the product of the torque and the angular displacement. In linear motion, the work done is the product of the linear force and the linear displacement. Similarly, in rotation, work done by a torque is the product of the torque and the angular displacement. So W rotational is tau multiplied by theta. Work done by a torque results in rotational kinetic energy. Is that right? Whenever you do work on an object, that work will be a measure of the kinetic energy of this object. This rotating disc has a kinetic energy. How do you define that kinetic energy? The kinetic energy of a rotating disc is a measure of the work done to give it an angular displacement or an angular velocity. So this W equal to tau theta is a measure of the kinetic energy of the rotating disk. The disk on the right is rotating with an angular velocity omega. Consider a particle of mass mi at a distance ri from the center. Well, this is a particle of mass mi at a distance ri. I'm sure you understand this concept. If that is the first particle, the mass will be m1 and the distance will be r1. If it is the second particle, it will be m2 and r2. We will take a general case where we consider any particle called the ith particle. Its mass is mi and the distance of that from the axis of rotation is ri. Therefore, now if its tangential velocity is vi, if this particle has, of course, any object that goes around a circle has a tangential velocity. We call it the linear speed. If vi is its linear speed or the tangential speed, then its kinetic energy will be what? What will be its kinetic energy? 1/2 mi vi squared. So its kinetic energy will be Ki equal to 1/2 mi vi squared. Well, this can be applied to any particle on the disk. Alright? But Vi equal to Ri omega squared, is that right? The linear speed equal to R omega, V equal to R omega, not omega squared. You need to make that correction. Vi equal to Ri omega. The linear speed equal to R times the angular velocity. So if you now replace this Vi by Ri omega, what will become? What will be the expression for kinetic energy? Ki now equal to 1/2 mi. Vi squared become Ri squared omega squared. Ri squared omega squared. Well, the kinetic energy of the rotating disk is the sum of the kinetic energies of all the particles which make up the disk. This is the kinetic energy of one particle. Therefore, the total kinetic energy of the rotating disk will be the sum of the kinetic energies of all such particles. So how do we write the total kinetic energy? K rotation. K rotation is summation I 1/2 mi Ri squared omega squared. Well, this 1/2 is a constant. I can bring it out of the summation. Omega is a constant. For all particles, omega is the same. The angular velocity will not change. Just like alpha is the same, omega is the same for all the particles on the disk. That means that is a constant which we can bring out. This will be therefore 1/2 omega squared comes out. And summation I mi Ri squared. What is the name of this quantity? This is a special quantity. We gave it a name. What is that name? Summation I mi Ri squared is the moment of inertia of the rotating disk about an axis through its center of mass. So this is I, the moment of inertia of the rotating object. Therefore, what is the equation for kinetic energy? Kinetic energy of rotation is 1/2 I omega squared. Now, do you see any similarity between this equation